And good evening again. Again, this is Scott Payne. This is my Math 502 final exam presentation, video 3. Let's go ahead and move forward. This is going to be over theorem 9.3.2, really finding the optimal interval. It could be, again, looked at like finding the shortest interval, but finding the optimal interval. So to begin with, let's kind of go back over theorem 9.3.2. It says let f of x be a unimodal, means single heel, PDF if the interval on the closed interval AB satisfies the interval from a to b f of x dx equal 1 minus alpha, part 1. 2, if the function evaluated at a is equal to that at b, and those two are greater than 0, and condition 3, if x asterisk is greater than or equal to a, less than or equal to b, it should be less than or equal to b. Where x asterisk is a mode of f of x, then this closed interval is the shortest among all the intervals satisfying I, or satisfying really one above. So I just took a typical unimodal distribution here. Here's our a and a b. They're at the same, f of a equal to f of b, both greater than 0. X bar being between that, so that's where the mode the most often would occur, so that's going to be the highest frequency. So we start there. Now, the example I was using really was using problem 9.41b out of the textbook and example 9.2, which utilizes 9.213. I will use the results of part A from that 941 to find the shortest 1 minus alpha confidence interval. So I'm going to let x follow f of x, where f is a strictly decreasing PDF on the interval half closed, half open, 0 to infinity. If x1 to xn are IID with a PDF of e to the minus x minus mu I of x. So the shortest 1 minus x confidence interval can be found by choosing B. Now again, we're running here from 0 to infinity, so my lower limit is 0. So now really what I can do is just set up here. This is part 1 of that theorem. So really all I need to do is find B. So based on example 9.213, I have a new random variable being the minimum, okay, of my x1 to xn is sufficient for mu with a PDF of the following. Right? So now I'm rewriting this. Now this is f cap y given mu. So now I'm going to have n e to the minus n y minus mu. Okay. So now the pivot, my pivot is just going to be my y minus u. So therefore what I can then say is the integral from 0 to b in e to the minus nt dt is just 1 minus alpha. Okay. And what does that leave me? Well, it's really kind of just a simple integration. We'll step through here. The pivot is t equal y mu. So I just set this integral up, 0 to b in e to the minus n dt, n e to the minus nt dt is equal to 1 minus alpha. So I just pull out the n, I integrate. I get minus 1 over n e to the minus nt. N's will cancel. Go through here and evaluate the limits of integration. So I end up having really 1 minus e to the minus nb equal 1 minus alpha. The ones we'll obviously subtract out. And drop the signs here, or divide through by -1 technically. Then I'm going to do the natural log of both sides here, and I end up with a minus nb is equal to ln alpha, or b is equal to minus ln alpha divided by n. What that does then, that tells me then that my shortest interval, because my a was a minimum 0, so my shortest interval actually in a problem like this is 0 to this minus ln alpha over n. So it's like a, b. And that's it. All right. Well, thank you so much, and love to have taken this class, and hopefully we can stay in contact. Take care, Ms. Goss. Dr. Goss. Bye-bye.